I have the pleasure of introducing Ms. Maria Gonzalez. She is a UNLV PhD graduate studying mechanical engineering. Please welcome Ms. Maria Gonzalez to SISTEM with a round of applause.
Thank you. So hello everybody. The name of my presentation is STEAM. So I'm sure you guys have heard of STEM before, but now we're trying to incorporate the arts, and I just gave away one of the answers for later, into STEM. So STEM really is the future of technological advancement. How many of you guys are interested in becoming engineers? Okay. Hopefully the rest of you guys will raise your hands by the end. So, like she said, my name is Maria Ramos Gonzalez, and I'm a fourth-year PhD student, and I should be graduating in about a year or so. I am a mechanical engineering student. I also did my undergraduate degree here, also in mechanical engineering, and I did the direct PhD program. So what that means is I was able to skip my master's and go right into PhD. So why did I become a mechanical engineer? First of all, I really like robots. I watched a lot of movies growing up, like The Matrix, AI, Bicentennial Man. I don't know if you guys have seen those, but you know, there are robots everywhere, and eventually I want to be part of the generation that starts making robots to hopefully do more of the dangerous functions that we do every day. I'm also into smart prosthetics. So if you guys haven't heard of that, whenever you lose a limb, let's say you lose part of your lower leg, there are a lot of advancements to prosthetics already. Your knee can have regenerative kinetic energy. That means when you bend your knee, it can kind of help you spring forward. The way that you design limbs can actually help boost a person. So a smart prosthetic is something that has either a sensor built into it, can power itself, and can basically do more than what your regular limb could do. And of course, I mentioned wanting to make robots like the robots you see in iRobot, that movie. They have artificial intelligence, so they can pretty much learn on their own. So I'm going to go over robotics, how I got to where I am today, and you guys will have an activity where I'll split you into different groups and you'll actually compete with each other. So here's a quick engineering overview, just so you guys can get a sense of what a mechanical engineer does. So civil engineers, we have that major here. They're the ones who run all of the building projects. So they make sure that the ground is stable, they make sure that you can run your pipes underground, they make sure that the sewer systems won't corrode. So pretty much everything in this building, around this building, needed a civil engineer to sign off on it. There's also computer science. So computer science is more software related. So whenever you run a program, a computer scientist built that program. You know, whenever you run video games, a computer scientist needed to know how that game was going to run. That goes hand in hand with electrical and computer engineering. So computer scientists can't do anything if they don't have a computer. So computer engineers are the ones who make all of the boards, who build the computers, who tell you what specs to run. Has anybody here built their own computer? Yeah, you have? So you're like halfway to being a computer engineer. And then there's me, mechanical engineering. So you guys know who that is, right? Yes. Well, it's Tony Stark and all the other ones that you mentioned. Tony Stark is a mechanical engineer. So whenever anybody asks, what does a mechanical engineer do? Basically, whatever he can do is what I would love to do. So I'd love to be Tanya Stark, you know? Maybe someday. Also, his father was also a mechanical engineer, just saying. Oh no, I gave away the answer. Okay, so what does STEAM mean? So for me, STEAM stands for Super Tactical Extraordinarily Awesome Magic. And I feel like STEAM is magic because you can make something out of nothing. I can sit down, draw a car, and have it built, I don't know, maybe in a year. But you know, you can go from nothing to something. You can take a few bars, put them together, put a gear on there, stick a battery in it, and make a little walking robot. That to me is magic. If you were to have done that back in the Salem era, you would have been seen as a witch. So it actually stands for Science, Technology, Engineering, Art, and Mathematics. And like I mentioned earlier, we've recently incorporated art into it because I, as a mechanical engineer, I know how to draw. I know how to put together all the parts that need to come together. I don't just buy, off the shelf. I don't go to Home Depot and buy a motor and buy gears and everything. There are certain aspects of engineering that allow you to be really creative. Also, if you're a civil engineer, you can create any bridge you want, right? But you need to know the materials. You need to know how to use the software. Again, something that computer scientists can put together for you. So if you really think about it, we need art and we need all the other disciplines within engineering to do our jobs. So I'll cover a little bit of robots. And a robot is just a machine capable of carrying out a programmed action. So you can program a robot, and if it doesn't have artificial intelligence, if you don't let it learn, you need to tell it everything that it needs to do. And these are usually really repetitive tasks that robots do. So these are the kind of robots that are in automotive manufacturing companies, right? They're the ones that drill holes all day, every day. They put the screws in. They weld parts of the frame together. This can also be seen as a robot because you load your program onto it, and it automatically prints something for you. So if any of you guys have a 3D printer at home, that's a robotic device. So there are 3 different types of robots. The first one is the one that does only what you tell it to do, which is known as a real-time, because it acts as soon as you tell it what to do, master-slave robot. So an RC car is an example of that. You tell it to go, it goes. You take your hand off of the remote and it stops. It doesn't keep going on its own. Other examples are like your drones. You have to tell them where to fly. Now this next one here, does anybody recognize where that's from? Yeah? I can't hear you. Yeah, from Toy Story. So this one is not quite a master-slave robot, because after you tell it where to go and you push the button for it to drop, the hinge drops by itself and picks up the toy, or doesn't pick up the toy, by itself, right? So that is known as a semi-automatic robot. So semi-autonomous robots are those that only need maybe half of the instructions. So something like the dump truck. The driver goes up to the dumpster, positions himself, pushes a button, but then this motion is done on its own. It's just automatic. It doesn't need to think. It knows exactly the path it's going to take. This one here is one of my favorites. It's called the Big Dog, and it's made by Boston Dynamics. Have you guys seen those videos? Yeah? So this thing, you can kick it, push it, it rights itself and never falls over. It's semi-autonomous. This by itself cannot go anywhere. It needs to know where it's going. So the concept was to have it carry a lot of the heavy things that soldiers have to carry, and it would follow the soldier. It wouldn't just roam off on its own. But it's semi-autonomous because the soldier doesn't need to tell it, okay, move this limb, move that limb, move this limb, or move that limb. It doesn't have to tell it, hey, you're about to fall over, right yourself. So that's a semi-autonomous robot. Now, there are also autonomous robots. And these are robots that don't need much instruction. So although these take a script, you pretty much just load it and it runs by itself, right? This one here just does whatever it wants, but after you've told it what to do. Something like this, something like the Roomba, you leave it in your house, and the way that it learns is that it bumps into walls. Just imagine that you're blind, or you're in a very dark room, and you have to figure out where you can go and where you can't. You have to learn that there's a wall in front of you. So this little robot goes around your house, bumps into walls, and knows, I can't go that way. Turns around, goes this way. If it bumps into another wall, it knows it cannot go that way. So it turns around, goes the other way. If there are stairs, and the sensor notices that there's sort of a drop-off, It knows not to go down the stairs. It's learned that in that location, there are stairs and it could fall and break itself. So have any of you guys heard of DARPA? Yeah, DARPA. So DARPA creates these challenges every few years, and one of the most, one of the most amazing things that have come out of DARPA is like the internet. So the internet was a challenge first created by DARPA, who can figure out how to connect everybody. So that was developed as a starting point through DARPA. Another one is self-driving vehicles. There was a challenge that DARPA put out that wanted to see who can have a vehicle drive itself from one point to another. So after that initial phase, everybody started doing it thanks to the initial push from DARPA. Recently, there was an earthquake in Japan where a lot of nuclear reactors were broken. And there was a lot of damage because of this earthquake. We as humans cannot just go into these nuclear factories and shut down valves, right? We would die, or we would get cancer and die very quickly. So DARPA put out a challenge to address this sort of need. How can we get somebody or something to take care of situations that are too dangerous for humans after an earthquake or a tsunami or any other natural disaster? So DARPA put out a challenge and called for universities, companies, anybody who could come up with a robot that would sort of mimic a fireman. So this robot was supposed to open doors, so first identify where the door is, open it, was supposed to go in, be able to pick up a drill, be able to pick up a saw, so that let's say the valve was behind a wall. Let's say that you knew the valve was behind this wall. Any fireman could come in, take the saw, cut a hole, and turn the valve inside. But how will the robot know how to do that? That was another challenge. The robot, of course, needs to go up and down stairs, because how do you get to these important places if you're stuck on the ground? Also, if there's been a natural disaster, the ground's not going to be even, right? There's going to be debris, there's going to be rocks, like doors that have fallen over. It needs to be able to climb or to get over those without falling over. So that in itself, I mean, even we would have trouble doing all of those tasks. But somebody like a fireman or somebody like a robot that doesn't get tired, the batteries may run out, but the robot itself doesn't get tired, right? And the robot cannot die of cancer. So I was part of a team here that participated in that challenge. And we actually started out with this robot here. Her name is Jamie, and she was about this tall. So when we first got her, she was broken. She had been in a presentation and had fallen off the stage. So we got her, and we started fixing her up. We fixed her ankles. We gave her little extensions to make her just a little bit taller. All of this exposed wiring, like all of this. Who takes care of things like this? Do you remember which major takes care of breadboards? Electrical and computer engineers, right? Well, we had to learn fast because most of our team was composed of mechanical engineers. We had mechanical engineers, a computer engineer, we had a computer scientist, but we all needed to come together and learn how this robot worked and how to fix her in order to make her move. So that's known as an interdisciplinary collaboration, right? So not just because I'm mechanical engineering means that I only know about mechanical engineering topics. And the more you guys branch out and learn about other fields, the stronger you'll be within your own field. So these were from different companies. These were from Robotics. And as you can see, even though they're leaning, they're like kind of hanging there, they're still taller than I am. Did any of you guys watch that movie Chappie? Yeah? You remember when they were getting fixed and they were strapped by their shoulders? That is actually the way that you hang humanoids. So those are known as humanoid robots because they kind of take the form of a human. And the reason why they have to be strapped up is if while you're fixing them, if there's some sort of surge, if they start to move, they could actually break. So if they're standing If their feet are touching the floor and they turn on and all of a sudden they try to right themselves, they could break their knees, right? If you're working on them and their arm is kind of like this, and when you turn them on, they go like this, they could smack you right in the face. So that's actually my team. There were more people working here, but this is my team. Now, I mentioned an interdisciplinary team, right? So we have me, mechanical engineer, computer science, mechanical engineer, computer engineer, and now these two here, one of them is sitting back there. She's actually a graphic designer. Yet she was able to work with us, even though she didn't know how to fix or build or program a robot, right? But we needed her. She was the one who designed pretty much everything you see on the robot. So let's say you're not interested in being an engineer. I won't be disappointed in you, but let's say your passion is art. You can be part of something like this. So even though you're not within the College of Engineering, if you're interested in art and still interested in technology, but think to yourself like, oh, I don't want to be the one coding it, or it doesn't interest me to get my hands dirty and get on the machines, you don't have to. You can sit on Photoshop and all the other programs that I don't know, but she does. So it took about 2 years to get to the point when DARPA announced the competition, and then finally everybody got together and competed. It takes a lot longer than 2 years to design and build a robot. So some of these were kind of already in the works. But how much do you think a robot like this costs? Any guesses? I need somebody to guess, so I can tell you you're wrong.
Like 100,000?
Higher. Higher than 100,000. $1 million! She already heard this probably. They cost around $1 million. Now why? Why do you think they cost so much? So why did you say $1 million?
Usually things like that cost a lot of money for all those parts.
Yeah, all the parts. So something like one motor is really expensive. If the motor in your car goes out, do you get a new motor or do you get a new car? I usually just get a new car because, I mean, I might as well, right? The motor is so expensive. These type of robots have a motor here, here, maybe here to do this. Definitely here, 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 here to move around. They have motors everywhere. Everything, every part of this robot is very expensive. And what happened to Jamie? Why did Jamie break? She fell. She fell from about this height. We don't break. It hurts, but we don't break. If these robots fall over, they break. But anyway, even though they were falling over, somebody made a really nice video for us to entertain ourselves with. And I'll let you guys watch it. So these robots needed to get through a door. So that robot's trying to get through the door. That robot's trying to walk over the debris. That one had wheels and couldn't roll through the dirt. So that robot thought it found that valve over there, and it started turning nothing. So that last robot, since it got out of the vehicle and made it within that square, did get the point. But as you guys can see, a lot of these robots are big and they're bulky. And if they fall, they usually break. And if they break, you're pretty much out of the competition. Because if they can't stand themselves up, let's say I fall over and I can't roll over and bring myself up, right? My shoulder's broken. I'll have to fly all the way to China or Japan or Korea, wherever they made my shoulder, and get fixed. So during a 60-minute competition, you cannot do that. You're pretty much out. So even though we laugh when these robots fall over, the people who were coding them and building them were not laughing. So I'll go a little bit over computer vision. So robots can do anything, right, if you tell them what to do. But they are much more powerful when you use computer vision, when you code them to see. Now, how do you make a robot see? How would you make your car see? I see you flailing there. You got an idea?
Maybe like radio waves that'll go out and then bounce back, and you can see like how far away something is.
That's one way.
I would guess like you put a camera on it.
Cameras.
Camera.
So that is one way of seeing. That's like how bats see, right? They use sonar. But I'm thinking more of cameras. So here's one quick video of how you make a robot see. And I have tutorials online that you guys can check out on my channel, Super Shock Labs. I highly recommend you all subscribe. And here I'm training my camera to see that green color down there. I have to filter it. So this is what the computer sees. It only sees yes or no, which is black and white, right? This is HSV, which is just another shade of colors. And on the bottom, this is what our eyes see. So here I'm filtering everything to tell my camera to only look for that green color. And everything is in real time. So I can actually pick up this paper and have it track just that color. And there are many applications for this. Let's say that you have a camera set in your backyard and you need to track your dog. So you can actually filter the colors to only spot, like let's say, the color of the fur of your dog, right? And you can always follow it around on your camera. And if you put a motor on your camera, it can actually pan around and see your dog. Another way that you can use cameras is to control the robot. So here I've split my grid so that each quadrant has a robot do something, some sort of action. And then in the middle, you always need a stop button. In the middle means stop. So I've filtered the color already to only follow that purple ball, and that'll be my control. So you can see that when I put it to different parts of the quadrant, the tank on that robot moves forward, backward, and then on the other side, it rotates left or right. By the way, all the code and everything that you need to know about this is on Super Shock Labs. Now, I spoke a little bit about drones, right? It's a real-time system. I won't go too much into drones, but that's also something else that I've worked on. I've worked on drones, I've worked on airplanes, and mechanical engineering, you do a lot of stuff. You do heat transfer, you look at how hot a fluid can get within a pipe, depending on, let's say you're working on some sort of ship, or even your car. How many of you guys here like cars? Yeah, have you worked on your car before? There, same thing. So you need to know how the fluids will impact the system, right? So mechanical engineers take a look at a lot of different things. And this is just one of the planes that I've worked on. And like I said, you can learn on your own. I have a lot of really nice videos on Super Shock Labs, but you can start with an Arduino starter kit. You can start to learn how to code using processing. That's free. You can download it for free. There are plenty of examples online. You can get a Raspberry Pi and, yeah, YouTube. I learned a lot of the stuff that I do off of YouTube tutorials. And here I'll just kind of go over some of this stuff. Having your knowledge and working on something outside of school, having hobbies and trying to learn how to do projects on your own can get you a lot of money. So here is me and my team, and we did a hackathon competition at CES. Have you guys heard of CES? Yeah, we were the grand prize winners, and we got $10,000. So you guys should start learning now and get rich quick. So my current work right now, mechanical engineers do a lot of stuff. My current work is in biomechanics. So I mentioned smart prosthetics, and someday I want to go from making just, even this is pretty smart. It has a load cell to let me know how heavy that patient is and how much force occurs at that spot whenever he makes a step. Hugh Herr over there, the director of the MIT Media Lab, he has the smartest prosthetics right now. So his ankle can actually regenerate power by itself. He never has to plug it in, he never has to charge it. It gives him a boost while he's walking. And if any of you guys know Full Metal Alchemist, that is my ultimate goal. Attach prosthetic limbs directly to the nerves. That way you don't need any external parts to control it. So yeah, that's about it. It's the end of my presentation. Oh well, that's the answer. All right, do you guys have any questions before we start the challenge? And
All do, all right.
Yeah.
Start it from the front. Come on.
I have a question for you, actually.
Yes?
You said you skipped your master's and went straight to your doctorates.
Yes.
How does that work?
So here at UNLV, by the time I graduated with my bachelor's degree, we had just finished a semester or two of that program. And many universities are trying this now where if you know you want your doctorate degree, why go through a master's? Go straight into your doctorate degree. It'll get you, a bachelor's can get you a lot of really cool jobs, but something that I was told is if you want to follow instructions, get your bachelor's degree. If you want to do a little bit more work and maybe head up some projects, get your master's degree. If you want to be the one telling people what the newest things in technology are, get your doctorate degree. Those are the ones who do the most research, those are the ones who drive the projects, and those are the ones who see what everything is being developed before anybody else, 10 years before anybody else sees it.
I have another question.
Yeah?
When you mentioned the camera and the color sequence, kind of like that, isn't there a lot of variables that come into that? Like, what if there's the same color in the
Yep.
kind of...
Yeah,
How
so
does that work? How do you know, like, the difference between this and that?
you have to filter it. So did you see how it's kind of
Yeah.
moving the bars? I look at the black and white and have it tell me when just that spot that I want to focus on is the only white part there. So if there are other little dots around, it'll grab the biggest one, and that's what it'll lock onto. So you put that in your code. You tell it, even though there are a bunch of little white spots here, look at the biggest chunk of spots and center yourself on that.
Actually, the question's for you. Once you get out of UNLV in college, what do you want to do as a job?
I'd love to work in industry. So when you get your doctorate degree, everybody assumes you're going to stay at a university or a research lab for the rest of your life. I want to go into industry, so I want to go into a company. I want to learn how a company works, and then eventually I want to make my own company, my own smart prosthetics company.
So you mentioned that you like AI.
Mm-hmm.
So you're more into like neural networks and AI learning on its own, other than just like pure hard-coded autonomous function?
Yes, so I did take a class here. The nice thing about going for your doctorate degree is that you can take any class you want, any upper level class you want. I took a neural networks class through the computer science department, and we learned about neural networks, and that's basic. So neural networks are just something that you tell it what you're looking for, you tell it what should be the outcome, and it just runs continuously and learns to get closer and closer to that outcome. You train it, and then you take out those variables, and it knows what to look for. So neural networks are part of AI. They're kind of like how our brain works. we learn what a spoon looks like. We learn how to differentiate it from a fork, right? So that's really simple, but that's on the cusp of AI.
So on the topic of prosthetics, you know how you said that the leg up there, it could, like, it would tell you the weight of, like, the person. Do you know exactly how it does that?
How does it do that? So that instrument, there was like a puck-shaped instrument right here, right on the limb. When that's compressed or pulled, it tells you how much compression there is. So it's like your bathroom scale. It's just in the shape of a puck.
So if someone was to like start out getting into robotics, is there like a certain like YouTube channel or a certain website you would suggest?
Yeah, mine. Definitely mine. Let me just remind you what it's called. There's mine. Honestly, I would just look, and then if you like the projects, even if the person doesn't have a lot of subscribers, if you like that project and they explain it well, go ahead and subscribe and stay up to date on what they do. There are a lot of tutorials on the Arduino website. So an Arduino is just it's a small microcontroller. It's not smart. You can code whatever you want with it, and there are kits. You can get kits to make little robots with it, and it comes with full instruction booklets. So that's what I like about the Arduinos. Whenever I teach, I teach anywhere from elementary school to high school. I start teaching them how to do robotics on their own, and I always recommend the Arduino. And I have them get the entire kit. It's like $100, but it comes with all the parts you need, and it comes with a step-by-step instruction booklet.
At my school, we have a program where you can use 3D programming. How does that relate to this?
3D programming? Are you talking about 3D modeling on the computer?
Yeah, we have a SolidWorks program.
Oh, you guys know SolidWorks already? We use that program all the time as mechanical engineers.
Okay, that's cool.
Yeah, so you'd already be ahead of the curve if you came to UNLV. But yeah, how that works is you start designing everything you need, and mechanical engineers, we look at every part of an object or of a machine.
Yeah, that's more mechanical engineering.
Yeah, mechanical engineers are the ones who use SolidWorks the most. All right, how many of you are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So a group of 3, another group of 3, right? That's 6. And then we need how many more? 2 groups of 4 and 2 groups of 3. Go. Okay, guys, the challenge. I'm going to time you guys. All right, the world is ending, and you need to pick one of you to be a robot, and somebody will write your instructions to get from here, from this point, out the door. How do you do that? How do you get me to walk from here all the way out that door? How many steps do I need? How much do I need to turn? Okay, those are hints. All right, go. 2 minutes.
So, alrighty, so first you gotta like walk out there. So if you take like...
Well, first you have to turn. Because
Okay, yeah, so if you're facing the door, you have to turn.
90 degrees.
So then okay, so like you gotta like have the hip roller like turn the like outward. So like you gotta like turn the hip.
Yes.
Motors.
As descriptive as possible. So not like all the way lift, but let's say like left foot, right foot, how many steps? How far do I turn?
Alright, and you gotta fix...
Whoever can give me the best instructions wins. If I don't know how far I need to walk, I'm never gonna make it out the door, right? Get up and check it out. Get up and check. Here, this is how big my steps are. Like this. I'm 5 feet tall. I don't know. No, one of you guys is gonna be the robot. One of you guys.
Oh, okay. Alrighty.
Get up and see how big. Get up and see how many steps you need. Right here.
90 left, forward, what's it, 5?
5. That's a 5.
And then 90.
Whoever can do it the fastest and the most accurate will win.
Right, and then, yeah, forward, 3, and then wait, you gotta push. You
have to lift your arms up and
Yeah, you gotta push. I don't think.
Lift and extend. You have to lift and extend.
Okay.
Everybody get your robots up here.
Alrighty.
But somebody from the team needs to read the robot instructions.
Okay. Alrighty.
And I'm going to time you.
Okay, that's good. Can we only move when they say the instructions? Or can we just kind of go?
I'll tell you start, okay? So the fastest team wins. All right. Who's your reader? Okay. Go.
90 degrees right.
Whoa, wait, stop. This is the robot, right here.
She stopped.
Whose robot is this? Okay, all right. Start.
Turn 90 degrees right, walk 4 steps. Turn 90 degrees left, walk 7 steps.
1, 2, 3, 4, 5, 6, 7. Stop.
Walk another 8 steps straight.
Oh. 1, 2, 3, 4, 5, 6, 7, 8.
Turning left, 90 degrees left, walk 5 steps.
1, 2, 3, 4, 5.
And that's how far we got.
All right. So 35.96. And they did not open the door. Next team. Christina, you need to watch and make sure they're not changing their instructions.
All right, take 90.
Whoa, I didn't say start. Start.
All right, turn 90 degrees to the right. Take 5 steps forward. Turn 90 degrees to the left. Take 15 steps forward.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I like how they get smaller.
Turn 90 degrees to the left. Take 5 steps forward.
1, 2, 3, 4, 5.
Turn 90 degrees to the right. Take 4 steps forward.
1, 2, 3, 4.
Push door.
Ow.
2 steps.
All right, 45 seconds. All right, so yep, you guys are the winners, and the concept was there. Push open the door, right? They needed to get through. So I have prizes for everybody, but where's my assistant? I'm gonna give all of you guys this flyer. This is for the multicultural program for STEM and health sciences. Even if you're not students here, you can always reach out to the director there and ask her about getting into the STEAM disciplines. So science, technology, engineering, art, math. All right, winners, come claim your prizes. Everybody clap for them. There you go. Congrats, good job.